Good morning, good afternoon, good evening, good night, depending on where you are in the world today. And welcome to our second RSC Sustainability Author Showcase. This showcase is coming as we come up to the end of our first year of publishing. And it's been such an amazing year. We've published 195 papers this year from over 30 countries, which is remarkable for a journal that is in its infancies. And of course, these studies all present an advance in chemistry that is also an advance for one or more of the United Nations SDGs. You're going to hear about 7 particular papers in a few minutes, and you'll be hearing from not just me, but also my colleagues, Professors Fran Curtin, David Cole-Hamilton, and Vincent Naimori, who will be speaking to you later. We've picked some papers, 7 papers for your attention, but I have to say that we are equally proud of all of those 195 papers. And a group of papers that I'm particularly proud of myself are the essays that have come from our early career researcher essay competition, which were titled, "How Can the Chemical Sciences Lead the Stewardship of the Earth's Element Resources?" And these essays are remarkable. I have to say, I learned from them. I didn't just judge them. And I do recommend them to you. In fact, the competition has been so successful that we've now just launched our second year of the competition with a new title, "How Can the Chemical Sciences Contribute to Decarbonising the Production of Energy and to Eliminating the Generation or Release of Greenhouse Gases from Large-Scale Manufacturing and Agricultural Process?" If you know somebody who is an early career researcher, we're broadly defining that as under the age of 35, please do encourage them to take part in this competition and to present an essay. But now it's time to move on to the substance of today and to the presentations of the papers that we have selected for you. And first of all, that is going to be by some pre-recorded videos. And so it will be for Dr. Ulf-Peter Apfel, who's going to talk about both sides matter, anode configurations after the activity of electrolyzers for organic hydrogenations. And so over to the recordings.
I'm working here at the Fraunhofer Society and also at the Ruhr University Bochum, so I have a double affiliation. And the great thing about that, and which also forms my research, I would say, and highly influences, is as a university, you're very much into basic research. And as Fraunhofer Society, which is an application-driven research institute, we are in the middle between research, or naturally a university, and industry. So, and this really pushes my research just to make chemistry and transform that into processes. So I'm from origin, I'm a bioinorganic chemist. We did molecule mimicking and so on and so forth. So, but now we transformed more or less into thinking about a catalyst. How can you transform that into an electrode, making the electrochemistry, and how to get that into a large-scale electrolyzer. So what my research is nowadays is really transforming catalysts into real life, and bringing them into real life scenarios into full-scale electrolyzers, which we do nowadays as well, because what we recognized is you have to optimize not only the catalyst, you have to optimize the electrode, and you have to optimize the full system. And we're doing that for the topics of hydrogen, CO2 reduction, and also electroorganic reactions, but also bioelectric reactions. Sustainability is of course one of the big things that we want to address. Sustainability, I think this is nowadays a little bit used as a buzzword. Actually, it's a very broadly used thing, which is undefined very often, I would say, which actually is not, because we have the 12 principles of green chemistry, and this in my mind also reflect the sustainability. I would rather speak about the 12 principles of green chemistry, because this is a more defined way to characterize sustainability. But what it counts all is that you optimize reactions to have less CO2 output, and you use resources in a circular way. So this is mainly what we think about. And if you're talking about electrochemistry, mainly what we do is how can you integrate power in form of any electricity to drive chemistry. And by doing so, of course, you have to use green power as well, sustainable sources. But when you do so, you have to think not only about driving this process, you also have to think about what are the compartments, what components you use, is that really green? And also you have to think about afterwards, not only to drive the chemistry, but also to think about what's about the purification. It might even be that we do an electrochemical process, but it's not more sustainable than traditional systems running on fossil fuels, because maybe in the aftermath, you have a purification step that is significantly less sustainable and will not allow just to get to the market and make an industrial application out of it, also for sustainability reasons. So I think in total, sustainability is you have to take this very careful in my mind, and you really have to think about the entire process, also including greenness analysis and LCA analysis, such as to characterize the process. Per se, I would never ever say we are just focusing on sustainability. We want to change processes. If it's more sustainable, great asset. If it's not, we have to think about how can we still use it and how can we make it greener. Let's say it like this. So, but talking just about sustainability is sometimes a little bit dangerous, I would say. At the moment, we are very much focusing on the CO2, electrochemical CO2 reduction. So what we do in this field is we have already small-scale electrolyzers with a diameter or a square of about 13 square centimeters. And what we're currently doing is we're building up a 1 square meter electrolyzer, which enables you just to transform about 100 kilograms CO2 a day. And that would be more or less the next stage, because we are making a stack, an electrocatalytic stack, which is like several cells that just put together, and use that more or less for going a little step further into industrial application. Because what we have also with industrial partners is when you have this small stack, you can just do a numbering up. Some of the basic engineering problems are already solved, and by the numbering up, you can make larger systems available. So I would say this is one of the main things what we're currently driving forward, just to get into application with some green solutions, let's say it like this.
So in this paper, what we did was use gas diffusion electrodes to convert CO2 and water to carbon monoxide and hydrogen. So hydrogen will act as a reducing agent for PEMs that we have, platinum group metals that we have in solution. So they will be reduced, and carbon monoxide will act as a capping agent. So at the end, our final products are PEMs nanoparticles. And then we can use this process to tune it to produce PEM nanoparticles with defined compositions. But we can also use this process to recover PEMs solution from a complex matrix, where we have not only PEMs but other metals. And because hydrogen at room temperature, because the process is run at temperature, it's only selective to reduce PEMs. We can recover selectively the PEMs and leave the other metals in solution.
Well, as you know, we are in an era in which we are changing from a set of non-renewable resources, which is basically fossil fuels, right, to another one where we are going to metals. We are shifting from using cars that contain catalytic converters to cars, for example, which are electric and so on. And then that means that in that change from one non-renewable to the other, we need to come up with technologies that allow us to recover such metals in a more environmentally friendly way than what we do today. Right now, we have a set of very large European projects. And these are all focusing on developing new technologies to recover different critical materials, critical metals sustainably. Especially we have two very large projects, one called the Peacock project and the other one called the Firefly project. And these both deal with recovering different metals, but specifically the platinum group metals from very complex streams. In the case of the Peacock project, we are recovering them mainly from leachates from catalytic converters, the ones that we use in our cars. And in the Firefly project, we are using it to recover from spent waste or off-specification catalysts from the chemical industry. So there, the application is that when these metals are leached in one or the other context, typically they are leached or present in solvents with a mixture of many other metals, sometimes 30 to 70 metals. And now we are applying what Omar, as the first author, reported in this paper. And we see that even from those mixtures, we can selectively recover 100% or near 100% of the platinum group metals without taking the other metals out. And that's, from the recovery perspective, the most important application, a selective method to recover these metals and in a context that they can pass from, again, a fossil fuel-based context, so the catalytic converter in a car, but then we can produce particles, like Omar will explain, that can be used for the green energy transition in fuel cells, for instance.
Yeah, so and also doing additionally, it's so I'm taking this process and I'm tuning it, not to recover the PGMs, but now you tune the process in order to have nanoparticles with a specific composition or with a specific size morphology, and I have already optimize the process, so we have already synthesized, for example, platinum unsupported platinum nanoparticles that we tested towards methanol oxidation, thinking about, for example, methanol fuel cells, which is it's a technology that it's lacking behind in for example, compared to hydrogen fuel cells, because methanol oxidation, it's a quite sluggish reaction. So we need to come with better catalysts. So we tested, we reported this work, and also in another journal of the Royal Society of Chemistry. We find out that we can synthesize, like, for example, unsupported nanoclusters that can because they have like a higher stability if we compare with, for example, with the standard catalyst. And now we are working also in not develop only like a monometallic nanoparticles, but mix them, or the PGMs, with platinum palladium, rhodium palladium, platinum palladium rhodium, to increase the potential activity. Right now, I'm using, of course, synthetic solutions, synthetic metals, but the goal is to use the metals that we recover from the from the waste stream solutions, purify the metals, and then use these metals to produce catalysts for further applications, and using exactly the same process, which we call them gas diffusion electrocrystalline.
Yeah, and in terms of the application as well, I mean, it's not only for the electrochemical applications, we can also go from the same application to the same application. So to give you an example, we have taken again the metals that are in the leachates from the catalytic converters, and we produce again a stream that can be reused on the catalytic converter producing process, the manufacturing process. And then they have compared some companies, for example, Ford and Fiat and Monolitos in Greece. There are different European companies. They have compared the performance of a catalytic converter using the traditional fluids that they use to impregnate the catalytic converters versus the fluids that we produce by our recycling method. And the performance of the catalytic converter is better when we use our recycling method. There are some impurities in the sample. We recover selectively the PGMs, the platinum group metals, but also there are some traces of other metals, and apparently that brings an extra added performance to the catalytic converter. So it's not only the fact that the process is electrified for the application, but the fact that we can upcycle a waste material into, again, a functional material for one or other application. Those are the two main features, let's say, of the application for whatever field we address.
Thank you to our authors for explaining a little bit more about their research. I'm one of the associate editors for RSC Sustainability, and as an associate editor, I was asked to talk a little bit about the research that I've been involved in editing those papers for. So the paper I'd like to talk about, the corresponding authors were Tom Farmer and Mike North from the University of York. And I can't see the slides that I sent in, so it's hard for me to note. There we go. Thank you, Jim. And they worked with a Brazilian team of researchers in this. And so I think a lot of our authors highlight responsible consumption as one of the UN Sustainable Goals that they're focused on with their research, which is really important, but there's so much more to that. And their work on making new materials from renewable feedstocks, they're also touching on partnerships for the goals, because they're working as a team. And it's important to think of the global impact of RSC sustainability and developing ways to tackle the UN Sustainable Development Goals through chemistry. So I want to tell you a little bit about the chemistry they're doing. And so they've been making some renewable polymers, cross-linked polyesters, and doing this, they've used locally sourced oils from plants, so nuts and some palm oils. And I think it's important for us all to consider that as we try to live sustainably, maybe we want to look at local solutions that can address some of these global problems. And so they took these oils and made them into epoxides. And they're not the first people to take this approach, but these are the first results for these Brazilian feedstocks. So in North America, people are looking, example, for soybean oil and epoxidizing that. So they co-polymerized this with anhydrides, and these anhydrides can be made from renewable acids such as succinic acid. And they do a co-polymerization. They use a urea-based non-metal catalyst and a co-catalyst that supplies the nucleophilic chloride ion that helps in the mechanism. So they optimize the conditions and were able to make these cross-linked resins as shown on the slide. And that's great, but it's no good if we don't know what the properties of these materials are. So they looked into the properties and characterized them. So one of the properties that they looked at was the hardness of the material. So this is something I haven't looked at in my own research, but I thought it was really interesting. And they showed that these new materials had similar hardness to materials used to make car tires and also the soles and heels of shoes. So it'd be interesting to see if they eventually get employed in that area. They looked at other sorts of typical properties for polymers, such as glass transition temperatures, decomposition temperatures, and a range of spectroscopic methods. Also, towards the end of the paper, they looked into the end of life of these materials by studying their degradation. And so in their degradation studies, they performed base hydrolysis reactions. They used potassium hydroxide. And this is in quite a simple fashion. The photograph that you're seeing, this is in the supporting information for the paper. And they found that 3 of 4 materials degraded very quickly. One of them took a little bit longer to degrade, and they did this just by looking visually at the appearance of the polymer in this aqueous potassium hydroxide solution. And I think there should be further research done in this area where they potentially look at the biodegradation, because if you can imagine, if they use this material in tires or shoes, there'll be particles entering the natural environment, and so there won't be potassium hydroxide there. So perhaps they can look at some fungi or other biological reagents to look at their degradation a little bit more. So that's all I've got to say on this paper, and I think we're going to hear from some more of the authors about their own work now.
At the moment, 35% of microplastic emissions that are being emitted to the environment are coming from textile waste, and this percentage will increase due to fast fashion trend. And there are several countries around the world that are currently reinforcing their legislation, mandating the installation of microplastic filters in every washing machine by 2030. And while this is a good initiative, they don't currently have a process to upcycle this waste or process this waste. And we are presenting a groundbreaking application of catalytic pyrolysis in order to upcycle these microplastics. And we are aiming to retain the carbon in a solid stage in order to avoid greenhouse gas emissions. At the moment, the fast fashion is emitting a lot of microfibers due to the shredding of these synthetic textiles, and they have dyes and chemicals that will damage as well the ecosystems and the human being, because we're breathing, we're eating microfibers that are actually everywhere in our world. What we vacuum as well, and they can damage of pulmonary system, and there are not a lot of research about how this damage will be in the future. As we increase the production of textile in every industry and we don't put a method to avoid their emissions, they will go all through all water system and to the oceans. As well, when we emit through air, they will end up in land, and then they will flow into the water system at the same time. We are demonstrating the simultaneous production of hydrogen and carbon nanomaterials from 2 greater microfibers present in the textile industry. While this is very important, we are moving forward the optimization of the process in order to enhance the cost efficiency and scalability of it. And in the future, this can be implemented in textile industries and near landfills and incineration centers in order to achieve circularity. This research directly aligns with the United Nations Development Goals of access to clean water, basically, because we are mainly focusing avoiding this emission into the ocean and the water environment.
Our paper we wrote was part of a lot of the papers that have come out in the last couple of years, which seek to connect the benefits of investing in sanitation services around the world to achieving other sustainable development goals, and those relating to agricultural productivity and also climate change as well. And we argue that if society can better recover nutrients from wastewater, society can also provide nutrients for crops and also mitigate climate change as well. I think that was kind of the key message of the paper, and that's the key message of a lot of papers coming out in this area in the last few years. There's been enormous advances in the kind of industrial, technological, chemical aspects of wastewater treatments and wastewater recovery in the Western world. And we see these great companies like Ostara and so on have have risen up in those places to recover things like struvite and apply it to agriculture at all. A current project, we look at wastewater for irrigation in Pakistan, in Faizabad in Pakistan. I think those kind of society, like those places are pretty far off this high-end technological innovation side of things. Recovering nutrients in some parts of the world would make a massive impact to farming. So that's like places like sub-Saharan Africa where fertilizer use is very low. You know, the potential recovery for crop nutrients in sub-Saharan Africa is actually massive, you know. But then if you go to somewhere like Eastern Asia where mineral fertilizer use is really high already, the amount that is potentially recoverable is actually far less, you know. So they stand to benefit, in Eastern Asia, they stand to benefit enormously by recovering crops just to prevent environmental pollution and mitigate climate change and so on. But the impact on crop productivity isn't really that much. Whereas in sub-Saharan Africa, it's absolutely huge, you know. So it depends on where you are in the world, really. Where we have a lot of technology, if we talk about technology and industry and so on in the West, really it's about how do we scale that up and how do we take it out of, like, you know, one where it's happening in one place at one time. How does it become national policy, I would say, is kind of the operative goal. Whereas the places like we work now in Pakistan and my new project, the question is really kind of not so much how can we treat wastewater to the extent that it becomes safe, because that's probably not a tenable goal in the short term. It's really more like, to what extent can farmers use wastewater without impacting on soil health and contamination and so on. Policies for sanitation in development, well, I think it should be, resource recovery should be a big part of it, you know. At the moment, a lot of sanitation development, it really just seeks to separate and to remove kind of urban populations from it, like, but there's no reason why we can't have resource recovery as part of it as well. So I'd say investment in sanitation should always kind of prioritize that as much as public health as well, because it has this effect on other things society needs, like improved food productivity and climate mitigation as well. Publishing with the journal was great. You know, we got some really detailed feedback and detailed corrections, which I think really improved the paper from people who obviously knew quite a lot about it. So no complaints on that end, I think, for me. And I think it certainly would be nice to see some innovations in the world of science publishing. You know, we're working on a model that seems somewhat outdated to me with the private sector, and also just with the kind of physical publishing as well, right? We kind of have to pay a lot of money for physical copies that, for the most part, we don't really use anymore. You know, it feels a bit outdated to me. So I would like to see some innovation in that regard as well. Yeah. One thing that we didn't go into in too much detail in the paper, because we felt like it was just putting too much into it, was accounting for the methane emissions from sanitation services around the world, which was part of the paper. We haven't talked about that now, but we also describes methane and nitrous oxide emissions from sanitation services around the world. And they're pretty non-existent in the West, where we have a closed sewer network, but in South Asia, Sub-Saharan Africa, Latin America, etc., where populations are reliant on more decentralized services like latrines and septic tanks and so on, these can cause significant amounts of methane emissions when they go anaerobic, and we identified that in the paper. But what we didn't identify is that converting methane into carbon dioxide equivalents is more complex than people realize, and because methane has this kind of temporal element, it breaks down in the atmosphere. The conventional metric doesn't really capture that temporal dimension. And what I've been reading with a colleague of mine in my new job is that to account for methane properly, you need to look at the rate of emission over the preceding 20-year period. Right? And essentially, it's good news for the most part. When methane emissions are constant or when they are decreasing, then the conventional conversion metric actually greatly overestimates the warming effect. But the thing is, when they are increasing, our conventional understanding actually underestimates the warming effect. And when they are increasing, the warming is actually much higher than we understand. And that's certainly what's going on in Sub-Saharan Africa and South Asia at the moment, where societies are urbanizing really rapidly and more people are turning up into cities and they're becoming reliant on these decentralized sanitation services. So I suspect that the methane emissions coming off latrines and septic tanks in many parts of the world is actually causing considerably more warming than people realize. And that's one of the reasons that we really need to invest in better sanitation services for the mitigation of climate change. And also to recover nutrients, obviously, because whenever carbon does not undergo anaerobic respiration and be respired in this way and become methane, it's carbon for recovery, which can be used in fertilizer production.
The rendering industry is a major part of our sort of food cycle in society. So this industry takes the materials that are left over from butchering applications, and so they take the parts of the animal that we don't typically consume. So hides and fats and guts and all of the bits that humans don't typically eat. That material goes to the rendering facility. It gets cooked and processed and in such a way that you separate the protein meal from the rendered fat. And that industry in and of itself plays an enormous role in terms of recycling otherwise material that we otherwise would discard. And so that and it's an enormous scale. So in the United States alone is something like 54 billion pounds of material a year that are processed by this industry. And so the materials that they isolate from the industry end up going into a lot of different things like animal feed and pet food. The rendered fats go into oleochemical applications. But one area that they have been using the materials for recently is for biodiesel and renewable diesel refining. And so this is obviously an appealing use for some of the rendered fat materials that they get, but the challenge is that because of the source material where they get the rendered fat, they tend to bring along a lot of dissolved light metals, and that becomes a problem when it's time to refine the biodiesel, refine the rendered fat into biodiesel, because those light metals can poison the catalyst that they would use in that process. And so it's a hurdle to getting these materials into the renewable diesel and biodiesel markets because the metal loads can be quite high at times. And so that's sort of where we collaborated with the industry to devise a tactic to remove those metals prior to entering the biodiesel and refining process. I appreciate the opportunity. And you know, the other thing we're finding with these materials, we can use them for a variety of other applications. The modifications that we do on the surface of the nanoparticles, we've applied similar chemistry to address odor. So small molecule odorants that are also associated with the rendering process. You can imagine that starting with the types of raw materials that they use for this process, there's a significant odor burden. And so the same materials do quite a good job of capturing volatile organics from the air. And then we've also looked at applications to remove and degrade pesticides and herbicides from water with the same materials. So it turns out they're quite versatile for a variety of applications.
A warm welcome to all of you who have joined us in this interesting and nice session again. I'm Vincent Nyamori from the University of KwaZulu-Natal. That's in South Africa, Durban, nice and warm. And I hope you're all enjoying the various talks. I've chosen to talk about lignin challenge in catalytic conversion of biomass solids into chemicals and fuels. This is a perspective article by Omar and Peter Ford from the University of California, where they're looking at utilizing non-fuel biomass for chemicals and liquid fuels. So we all know that climate change is a big issue. That's to humankind and also to the sustainability of our ecosystem. Currently, excessive generation of greenhouse gases, that's your GHG, in particular CO2, is causing a lot of concerns. There are three main influences that causes this emission. Firstly is the energy production. That's where we look at fossil fuels being used, such as coal, natural gas, and petroleum for production of electricity in particular. There are alternatives to this. There's solar, there's geothermal, there's wind. All this trying to decrease the negative impact of the GHGs. The second big contributor to greenhouse gas, in particular CO2, is your transport sector. You're looking at about 1.4 billion internal combustion engines running around the globe. And these are all fueled by fossil-based liquid fuels. The good thing is that currently there are new cars. At least in 2022, we are seeing about 13% of sales coming from electrical vehicles and the hybrids. So there's some positive initiatives by government, by private sectors to reduce our greenhouse emissions. The last but not least is our aviation, our international shipping, which contributes to the GHG emissions. Unfortunately, in this sector, there are not many viable alternatives. Solutions, the alternative to production of liquid fuels, one that people have tried is electrochemical CO2 reduction. However, this approach is very expensive with a lot of energy requirements. So this manuscript, that's why I chose it, looks at the opportunity to convert lignocellulose, that's your carbon neutral alternative, to liquid fuels or to high value chemicals. And when you look at this case, they're looking at particularly using non-food biomass feedstock. We're looking at agricultural or waste from forestry. So why lignin is a question. Firstly, its abundance. Its second most largest component of the wood apart from cellulose. And then thirdly, we get your hemicellulose. The second reason is because it's richly functionalized. It composed of these aromatic monomers which are linked and cross-linked. So why are we not using lignin? The challenge is separating the monomers and maintaining or retaining the same functionality produce fine chemicals for our industry. Also, you're looking at these monomers and trying to reduce them and separate them to introduce long chain 9 or 10 carbon chain that can be used as our liquid fuels. So reducing functionality in lignin is also an economic challenge for our biorefineries. The solution is such that when you look at this paper, they talk about novel catalysts need to be looked into. We need to introduce novel catalysts and also understand the mechanistic insights on how we can get to low temperature depolymerization and selective deoxygenation to give you fragments that are useful for either as fuels or as fine chemicals. And when you look at what they looked at copper-doped magnesium or aluminium-based catalysts, which they try to disassemble this lignin with the help of methanol, particular methanol in particular, to get cyclohexanol products with very little char. Char is a big problem. It has not much value in terms of a chemical. They have also looked at hot acidic methanol, and in addition to that, they have introduced dimethyl carbonate as a co-solvent, which provides a more selective monomer, and that's the ideal of what you want to do. They have also introduced heterogeneous transition metals, your palladium, platinum, rhodium, and ruthenium, which converts this lignin to more specifically to phenolic monomers. So depending on the catalysts that they used and condition used, they increased their selectivities to phenolic products, which had a very high chemical value. Some were used as fragrance, and some could be used as flavors. So they were also able to tune this catalyst to afford our C9, which is a good source or precursors to our hydrocarbon fuels. So what are the prospects that comes out of this paper? What are the impacts? The author suggests that we need to look at moderate-sized integrated biorefineries in regions where there's agriculture, forest waste, all being integrated together. So what does that have in terms of impact? We are looking at there will be redistribution of industry activity and wealth. That's from cities into the rural communities. And that's a major positive socioeconomic outcome. Importantly, it will also reduce our CO2 burden without compromising food supplies and also affecting our natural ecosystem that we need to cherish. So I find this article very interesting, innovative, very optimistic, and I'm hoping that one day we'll be able to produce fine chemicals, and importantly, we'll be able to see our aviation, our shipment fairly transformed from what it is to where we can actually reduce our CO2 emissions from them. So I will encourage everyone to read this article by Abu Omar and Peter Ford. And now I want to introduce you back to our editor, RSC Sustainability editor, Professor Tom Welton, who is also a professor of sustainability at Imperial College London. Professor Tom Welton.
Thank you very much, Vincent. And thank you to everybody who's presented today, either in person or on a recording. And they told us about 7 absolutely fantastic papers that we have published. And, you know, from synthetic electrochemistry through biomass utilization and the circular economy, they really do demonstrate the role of chemistry in enabling a sustainable future. And I think one of the things that I find myself saying a lot is that people have to realize the decision to defossilize the chemicals industry has already been made. As we move away from fossil fuels, we have no choice but to look for new sources of carbon. And things like CO2 or biomass will be the sources of carbon for the future chemicals industry. So the question isn't so much whether we will achieve this, but how we will do it. And that is the thing that I think these papers have really contributed to. How are we actually going to do this? And I think one of the things that's really important, well, for us at RSC Sustainability, but also generally, and that's, you know, not backing single horses, not thinking that technology has to be, this technology will win out over that technology. What is really, I think, going to be the future of the chemicals industry is that in different places and at different times, different technologies will be more or less appropriate depending upon where you are. And so then there's not a competition in some head-to-head race. Both technologies, both types of technologies can flourish. And I guess that's actually, you know, I mean, it's really just last week, we saw the first transatlantic flight with an aeroplane entirely fueled by biofuels. And, you know, one flight does not a sustainable industry make, but it's a huge advance over where we were just a few years ago. The other things that we've heard about today, you know, which I think, again, is a really important way of viewing what we now call the circular economy, which is that thinking about current anthropomorphic materials as sources of carbon and other renewable materials. There's an awful lot of anthropomorphic carbon mass out there that is a potential resource for the future. So you don't just have recycling. I think what was really interesting in that paper was that you had upcycling to a product that was more valuable than the source material itself. And of course, we also heard about the importance of clean water, which is a fundamental need for a healthy future. And wastewater treatment is a crucial technology. And what we saw today was that that public health need of producing clean water can go hand in hand with resource recovery from the wastewater, and with innovation in that area, that actually the cost burden of good sanitation and good wastewater treatment can be reduced by the recovery of valuable materials from the wastewater. So one of the things that I'm constantly asked to do, which is to define what we mean by sustainability here at RSC Sustainability, and we really do try to hold away from that as well as we can, because we do not see ourselves as the arbiters, and certainly not the police, of what is or is not sustainable. What we rather see is that RSC Sustainability is a means to facilitate this discussion. It's for you to explain to us and our readers how your research represents an advance in chemistry and also an advance in one or more of the UN SDGs. So it's really important to focus on the sustainability spotlight statement as a central part of your manuscript. And what I really liked in Fran's presentation is that she gave an excellent example of where the authors have thought beyond just saying SDG 17, responsible consumption and production, but really thought about how their research positively impacts other SDGs. And I really would encourage you to do that. As we move on into next year, one of the things that we'll be doing is having some theme collections that we've planned, and they are open for submissions now, and they include energy materials redesign, reuse and repurposing, CO2 conversion, and the broader circular economy. And so from that, my next delightful role is to introduce to you David Cole-Hamilton, who's going to be talking about some of the editorials that we have held about the SDGs. Over to you, David.
Thank you very much, Tom. And I do want to pick up from where you left off. I don't know how to get my screen. Will you put my screen on there, Jim, please? Because what I'm going to do is I'm going to talk about two of the editorials that we've done. The editors, the associate editors, are trying to highlight various different to highlight various different of the Sustainable Development Goals. And I'm going to talk about one that I talked about. I think you can see them on the screen now. Sustainable Development Goal 2, Zero Hunger. And Martin Prechtel, who can't be with us today, wrote one on hydrogen storage. And it's extremely related to what we're doing, because to what I'm going to talk about as well. So I'm going to talk about them both together. There'll be another one. Fran has done one as well on clean water, but life in water. But let's talk about these two. And the thing that really occurred to me when I was doing this is that when you start to think about how to tackle these goals, you find that you're actually tackling more than one at the same time. So let's look at what I want to talk about first, which is the Zero Hunger Goal 2. And I want to talk about it by talking about the Haber-Bosch process, which is a chemical reaction where you take nitrogen from the air, react it with hydrogen, and make ammonia over a catalyst. And this is used for making fertilizers. And this is the most important reaction that chemists ever do. It's a huge reaction, 176 million tons a year. And it's astonishing thought that 80% of the nitrogen in our bodies, in the amino acids and in the proteins, come from this reaction, not from natural sources of nitrogen, but from this reaction. Amazing. And that, together with all the other agricultural chemicals that we have, allows about half the world to be fed. If we didn't have agricultural chemicals, we would not be able to feed 4 billion people. So it's incredibly important to life on the Earth. But it does have some disadvantages. One of them is it uses about 1.8% of all the world energy supply. That's extraordinary. It's the equivalent to the amount of energy used by 144 million people in a year. So really huge amounts of energy. The other main disadvantage comes from the way you make hydrogen. So at the moment, it's made by steam reforming of methane, I show you here, which produces carbon monoxide and hydrogen. The carbon monoxide then undergoes something called the water gas shift reaction, and it produces more hydrogen and carbon dioxide. And that carbon dioxide is vented to the atmosphere. And 5% of all the methane consumed in the world is used in this one process to make the fertilizers. And all of the carbon in that methane is thrown away into the atmosphere. And it's responsible for 1.8% of our carbon dioxide emissions. So this is huge. These are huge problems. These are problems we need to tackle as chemists in order to reach the Sustainable Development Goal. Now, one way to do this, to get around the problem of the carbon and the carbon dioxide, and indeed much of the energy, because those reactions are carried out at very high temperature, would be to do efficient water electrolysis or photolysis. And that's what I'm going to talk about. That's what Martin was talking about. And we need also to make improvements to the catalyst if we can. And some work is being done on this by various people around the world. So let's now shift to clean energy, which is what Martin talked about. Oh, sorry, before I do that, there is another problem with ammonia, not just in making it, but in using it. So here's a river, which is suffering from eutrophication, which is caused by ammonia running off and phosphate running off into the stream. It causes algal blooms to grow, this green stuff, and that prevents air from going through to the bottom into the river, and it kills all the plant life and all the fish in the river. So this is a very, very serious problem. We have to do something about it. The reason for it is because we're using much too much ammonia. When we spray a field with much more than we need. And what we need to do is to think about how we can target the ammonia to the plants that need it. So if you can have a little drone that goes across and says, there's a sick plant, you need to put ammonia on that one, and there's another one, but we don't need to put it on all of them, then that would be an amazing advance. Now, I'm not saying that's how it will be done. Here's a drone actually spraying as well, which I don't think will be done. Ammonia also causes air pollution, greenhouse gas formation, and ozone depletion. So I've written here partnership for the goals. It's really, of course, we're not going to be able to do this by ourselves. We have to collaborate with with agriculturalists and farmers in order to reduce the amount of ammonia we're putting on the fields. Now, let's talk about affordable and clean energy. This is what Martin wrote his editorial about. We need to have renewable energy. We can't go on using fossil fuels. We all know that. And the only source of energy coming into the earth is from the sun. And in this picture, you'll see plants growing. That's photosynthesis. That produces biomass, which can be used for example, biomass burning plants, or it can be used for wood burning stoves and so on. That's one way to do it. When the sun lands on the earth, it warms it up. That makes the air above the earth hotter, so it rises and winds form. So wind is a form of solar energy. If winds pass over the sea, then you get waves. So wave energy is a form of solar energy. If the water is evaporated and falls as rain, you can have hydroelectric power. So all of these are from the sun. And the only one that isn't in this, and then photovoltaics, where you have solar panels, of course, they're also directly from the sun converting into electricity. The one in the front of this picture is geothermal energy, very important in some places, especially Iceland. Not renewable, but there's so much of it that we don't need to worry about it, and it isn't from the sun. And then there's nuclear energy as well, of course, which does not release carbon dioxide or greenhouse gases. And then, however, so we use all these methods, and they work, and we're producing a lot of renewable energy. But sometimes, even on a windy day, windmills are standing still; they're not spinning. And this is because they're producing too much electricity, and we don't know how to store the electricity they produce. And in fact, in 2022, the UK paid 125 million to stop wind generators. They paid the owners to make them not generate wind. And this is tremendous waste. So what Martin was talking about was, how do you store this energy? Well, one way would be to use pumped hydro, where you take the water from the bottom of a hydroelectric plant, you pump it back up to the top, and it comes back down and generates hydroelectric power again. And this works very well, but there are only a limited number of places where you can do that. And so that's not probably going to be a major contributor. In principle, you could use batteries. But if you had, at the moment, in terms of wind power, we have about 966 gigawatts around the world that need to be saved. This would require 3 tons of lithium, 3 million tons of lithium, which is 5% of all known resources, and 20%, 20 times what we currently progress. And then we need to take the gigawatts up to terawatts, 10 times what we're doing at the moment. So I don't think, and Martin doesn't think, that batteries are the answer. And he comes back to hydrogen, and this is where the two overlap very strongly. Could we make our energy from hydrogen? Well, in principle, we could. At 10% solar energy conversion, you could supply all of the world with all its energy needs from an area the size of Libya. Now, I'm not suggesting that, but I'm suggesting that all the deserts could be used as solar energy collecting places. But it's the storage and conversion storage that's the problem. Now, one thing about this, I've mentioned water electrolysis already, but if you could electrolyze, well, sunlight has enough energy to break water down into hydrogen and oxygen. It doesn't happen, of course. But if you put a catalyst in, you can make it happen, or by electrolysis, you can make it happen. And then when you burn the hydrogen, you get the water back again using up oxygen. So this is a totally circular process. This is a real example of a circular economy. So this is very, very important. So using overproduced electricity. So when the wind's blowing and nobody's needing the electricity, or when the sun's shining and you don't have enough, or there's wave power, tidal power, any kind of power that's overproduced, then you store it as hydrogen by this electrolysis process. Now, this is what we do at the moment. I've mentioned the top reaction already. That's the steam reforming of hydrogen and water gas shift reaction. And we are producing about 70 million tons a year and releasing all the CO2 in the atmosphere, as I've already mentioned. By 2030, we will be using blue hydrogen. We could be using blue hydrogen. That's exactly the same process, although instead of pumping the CO2 into the air, we put it into old oil wells or old coal mines. This is called carbon capture and storage. So far, there's very little of that done in Europe. There are plans to do it, but it's not done at the moment. But green hydrogen, the one on the right here, is where you electrolyze water to produce the hydrogen. And we will need to have an enormous amount of this because we're talking about 150 to 500 million tons a year. Huge. But we do need to place platinum, and not infrared, but iridium, sorry, by 2030. By 2050. So this is going to be a really important thing to do. It's going to help the ammonia production, and it's going to help our energy production. Now, here I've summarized exactly what the ammonia problems are. So we see the ammonia, the nitrogen and the hydrogen being made by steam reforming. And then we see the ammonia, too much going on the land, feeds 8 billion people, but then you get the eutrophication as well. So what we're doing, this process causes zero hunger. There is hunger in the world, but that's because of distribution, not because there isn't enough food. So this tackles the problem of zero hunger. And as I said before, if we get rid of the steam reforming and replace it with hydrogen, that's also part of affordable and clean energy. But there's so many more sustainable development goals involved here. So we've got to have partnerships. I've already mentioned that. We've got to work with all kinds of other people, engineers, agriculturalists, everybody to do this. And then, of course, if we're doing this, we're being responsible in our production. So this is responsible consumption and production. And this will lead to work. It will lead to a lot of work, and it'll lead to a lot of work all over the world. So this is decent work, and it will lead to economic growth. And we will need everybody to do this. So we will need men and women, and there are different ways of looking at problems. It's tremendously important. So this will lead to gender equality. And in order to do it, for these people to do it, the million jobs that we have to create for making hydrogen, for example, we have to teach people how to do it. So this will improve the education of people in a sustainable way. Of course, because we're not generating CO2 anymore, or reducing the amount of CO2, that's part of climate action. We're mitigating climate change. Because we won't be polluting the seas if we put the ammonia on properly, then life below water and life on land, there'll be less pollution and will be improved. This will lead to good health and well-being. There won't be the problems coming from these things that we're doing before. And of course, our cities will become more sustainable. Industry will have innovation in industry. It'll be very successful. We'll have reduced inequalities because this will be all over the world. This won't just be where the oil is. We'll have small plants doing this all over the world, and so we'll have much less inequalities. And that will lead to less poverty. And because wars are fought over coal and oil at the moment, that's one of the reasons we don't have enough peace. If we don't have coal and oil, we have a distributed system, we'll bring peace and justice. Now, the one I haven't mentioned is clean water and sanitation, but of course, if we're not polluting the water, it makes it easier to clean up, and we will have better water as a result of this process. So you can see that just tackling one or two of these sustainable development goals will lead to helping to solve or approach all of them. Thank you very much.
Thank you very much, Dave. Do you need to go and sort your door out?
I've got someone knocking on my window. I did make
Was that what it was?
Excuse me, 1 second.
Okay, of course, David, of course. Well, in the meantime, I mean, let us talk about that amazing presentation from David. And I think it really did highlight what I was saying about the sustainability spotlight. If you think through the consequences of the application of your technology and your work, then it is seldom that there is only one SDG that you contribute to. I don't know, Fran, Vincent, what do you think?
No, absolutely. They're so intertwined with each other, the SDGs, and I encourage our authors or scientists out there listening to go and have a look at the UN website and to dig down behind. There are targets behind each of these SDGs that can be addressed through many different scientific disciplines, including chemistry.
Yeah, I agree that, we talk about the goals a lot, but looking inside the goals at the targets is a vital thing to do as you try and develop your technologies and think about ways in which you can positively impact on those goals. Welcome back, David. Vincent, what do you think?
Sorry about that.
That's all right.
True. I mean, if you look at one SDG, one way or another, it affects the other SDGs. So they are not in isolation, they're not in silos. So whenever you do research, you'll discover that you actually have to mention 2 or 3 impacts that it has. And that's just the nature of how these things are very interlinked.
So, David, one of the things that I was thinking as you were giving your presentation, you were talking about the role of hydrogen as the energy storage medium. And I've seen papers where people have talked about using ammonia as the energy storage medium. Have you got any thoughts on that?
Well, it is possible to make to store hydrogen as ammonia, as you've seen how you make it, and there are reactions which reverse it. And I think one of the things that people are talking about is because the energy density of hydrogen is difficult, you have to have it at high pressure, and you can have ammonia as a liquid, and it has not a very low boiling point. Then in ships especially, I've heard people talking about that as a possible way of running ships. Because ships are difficult, having you can't plug them into the lanes to charge up a battery or anything like that. So particularly if they're going long distances. So I've heard people talking about that, and I think it is an interesting idea. I don't think it's fully developed yet, but it is an interesting idea.
But another front on which to push. Okay, so I mean, really what I need to do is to thank everybody for their contributions. Is there anything anybody wants to chip in before we all carry on with our days? So finally then, thank you to everybody who contributed today, but also thank you to all of our readers, and and by virtue of the fact you're listening to this webinar, you are one of our friends. So thank you very much for being one of our friends and supporting us in this first year of RSC Sustainability, and I look forward to working with you all in the upcoming years to grow the journal and to see so much great research again. And very finally, Happy New Year, everybody.
Thank you.